Okay, so let us continue. So yesterday we have seen the IV characteristics of PN junction. Okay, so we have seen that how current flows in forward bias and reverse bias. Okay, so you get I forward bias, you get exponentially increasing current, and in reverse bias you get very minimum current. Okay, and this is your breakdown voltage. So in reverse bias only your reverse saturation current flows. Now I want to discuss temperature effect. What happens when you increase the temperature? Okay, so when I want to discuss temperature effect, okay, so first we'll see
सर आवाज नहीं आ रही।
सर आवाज नहीं आ रही।
आवाज आ भी नहीं रही।
हाँ 1 मिनट रुक जाओ।
am I audible now?
Yes,
Yes,
sir.
Okay, so I'm discussing the effect on temperature on IV characteristics. Okay, so reverse saturation current. So as I increase the temperature, my reverse saturation current increases. Okay, if I increase the temperature, my reverse saturation current increases. So say this graph is on temperature T1, this is on T2, okay, and this is on T3. Okay, so when I increase the temperature, T1 T3 is greater than T2 is greater than T1. So when I increase the temperature, my current also increases. Okay, so current become reverse saturation IC3 IS3 is greater than IS2 greater than IS1. Okay, so your reverse saturation current, okay, increases with increase in temperature, and the same time you can see your breakdown voltage. Okay, your breakdown voltage also increasing. Earlier it was here, so so as you increase the temperature, okay, T2 and T1, okay, your breakdown voltage also, say VB3 is greater than VB2 is greater than VB1. Okay, so this is your avalanche breakdown voltage, avalanche breakdown, okay, voltage. So your breakdown voltage is increases. We'll discuss now why it increases. So now what happens, your cutoff voltage, so cutoff voltage decreases. So this is on T3, this is on T2, this is on T1. Okay, so your cutoff voltage decreases. Okay, forward current increases. Okay, breakdown voltage, if it is avalanche, then it increases. If it is linear, then it is decreases. Okay, this is avalanche breakdown. Okay, so voltage for avalanche breakdown voltage increases. Okay, so now why it happens so for that we have to see the expression for reverse saturation current, how reverse saturation current increases with increasing temperature. Okay, so let me write the expression for reverse saturation current.
Please don't drop that points.
Yes. Okay, so you can note down this point.
cycles.
Okay. So can I erase this one now?
Yes.
erase कर दो इसको, this part. Okay. So let me explain these effects one by one. So I'm erasing this one. Okay. So what happens when you increase the temperature? Okay. So when you increase the temperature, what happens? Your intrinsic carrier concentration increases. Okay. So you have the expression for reverse saturation current is given by IS. Okay. That is given by area. This depend on area of the junction. Okay. Ni square. And then you have diffusion coefficient. Okay. Diffusion length for electron, doping Na. Okay. Plus you have dp, okay, nd, dp, lp, okay, and your nd. Okay, so just let me check whether is nd or na. Okay, so okay, just for the moment write this. I will correct this one. What is nd or na? Okay, so I have to check this one expression. So this is current. So IS basically reverse saturation current basically depends on your intrinsic carrier concentration. Okay, and we know the intrinsic carrier concentration itself is a function of temperature. Okay, so we know as temperature increases, okay, my ni increases. Okay, as temperature increases, my Eg also decreases, band gap also decreases. So as I increase temperature, the intrinsic carrier concentration increases, Eg decreases. So the overall effect is your IS increases. Okay, so your IS get increased when you increase the temperature. Now once IS is increased, okay, once IS is increased, then of course your forward current will increase. So how much IS is increased? Okay, so it is observed that your IS reverse saturation current, reverse saturation, okay, current increases by 7%. Okay, 7% per degree per degree centigrade increase in temperature, per degree centigrade increase in temperature. Okay, what do you mean? That you are, if you increase the temperature of junction by 10 degree, so per degree centigrade increases by 0 by 7. Okay, now you increase by 10 times 10 degree. Okay, so it comes allowed almost twice. Okay, that means your reverse saturation current, okay, reverse saturation current, okay, doubles, okay, for every 10 degrees centigrade increase in temperature. Okay, 10 degrees centigrade increase in temperature. So if I write now the expression for IS, reverse saturation current, is a function of temperature. So I can write that my IS2, okay, is equal to IS1 2 minus T2 minus T1 divided by 10. Okay, so whenever the difference is 10, okay, difference is 10, my current become double. Okay, so this relation, important relation, you should remember. Okay,
Sir, is this 2 multiplied by?
T2 power T2 minus T1 upon 10. Okay, so where IS1 is what? IS1 is the reverse saturation current. Reverse saturation current at temperature T1. Okay, T1 degree centigrade. Okay, or Kelvin also you can write. Difference is same always. And IS2 is your reverse saturation current at temperature T2 degree centigrade. Okay, so if you have some current, some
सर वो परसेंटेज का मतलब नहीं समझा, कैसे लिखा हमने 1 पॉइंट?
अरे भाई हर डिग्री सेंटीग्रेड के लिए सपोज आपकी करंट 1 है. ओके, सो आपने टेम्परेचर 1 डिग्री इंक्रीज किया, आपकी करंट हो गया 7% इंक्रीज हो गया, दैट मींस 1.07 हो गया. ओके, अब अगर अब आपने फिर इसको फिर आपने एक डिग्री बढ़ाया, तो इसका 7%, इसका 7%, आपका इनिशियल है 1.07. ओके, अब इसका 7% फिर निकालना है. फिर जैसे हम लोग वी कैलकुलेट द इंटरेस्ट ना, इन इंटरेस्ट. Okay, so compound interest. So similarly, every degree, like every year you increase your interest increases, compound interest. So here also for every 1 degree your temperature your value of current increases by 7%. So this is roughly equal to, if I 10 time increase this one. Okay, if I increase 10 time, roughly this comes out double. Okay, so for this is roughly only. Okay, so you can put here roughly. So your current becomes doubles. Okay, if you do 10 times 7%, 7%, 7%, 7%. Okay, so it comes out almost 2. So your current becomes doubles at every 10 degrees.
Current increased 10 means 10 times we have 10 degree we have increased.
Yes. If you increase, difference is 10. 10 divided by 10 is 1. So IS2 become 2 IS1. That means current getting double. Okay. So this was current. Now we know if current increases, then of course your forward current also increases. As I told you, temperature increases. Okay, temperature increases, so your barrier width decreases. Barrier width decreases. Okay, that means W decreases. Okay, so when your T increases, your Ni carrier concentration increases. Okay, your width go down, barrier width go down with increase in temperature. Okay, because now you have more Ni, you have more charge carriers. When W go down, your VBI, okay, your cutoff voltage also go down. Okay, so we can write cutoff voltage decreases, okay, by minus 2.5 millivolt per degree centigrade. Okay, so as you increase the temperature, suppose you have a 0.7 volt, so silicon cutoff voltage 700 millivolt. So if you increase the temperature, it will go down by 2.5 millivolt. Okay, so it become, if you have a 700, now it become what, 697.5 millivolt. So every degree centigrade increase, your cutoff voltage decreases by minus 2.5 millivolt. Okay, and the third point is your, what is third point? Third point is forward current. Okay, so forward current also, when you increase the temperature, barrier width decreases. Barrier width decreases means now your forward current increases. Okay, if increases. So if I plot this one, okay, so you can see this is my I, this is my V, and you see here this cutoff voltage is getting decreased when I'm increasing the temperature. Okay, and current also increasing. At lower voltage, I'm getting same current. Okay, so this graph is going minus 2.5 millivolt per degree centigrade is going this side, with increase every degree centigrade increase in temperature. And similarly, now for this voltage, you're getting this current. Okay, So you're at a lower temperature, you're getting this current at this voltage. For higher temperature, the same current you're getting at lower voltage. That means your forward current also increases with increasing the temperature of your junction. Now the important point is here, breakdown voltage. Okay, we call it avalanche breakdown voltage. So breakdown voltage also increasing. Okay, so that we have to explain why breakdown voltage increases with increasing temperature. Okay, so the next point is breakdown voltage. Okay, so can I erase this one? This point is clear what I'm saying?
Sir,
Reverse saturation current
sir,
increases.
वो
Okay,
forward
forward current,
forward current का एक और बता दो.
फॉरवर्ड करंट से क्योंकि विड्थ कम हो रहा है ना, बैरियर विड्थ कम हो रहा है, बैरियर विड्थ कम हो रहा है, कनेक्टिव आपका कैरियर व्हेन यू इंक्रीजिंग इंट्रिंसिक कैरियर कंसंट्रेशन इंक्रीजिंग, more charges produced, conductivity increases. Okay, so obviously your this temperature more, that means electrons have a now little bit more kT, more energy. So more energy means now they can easily compared to earlier case, they can easily pass through the barrier. Okay, width also decreasing, band gap also decreasing, energy becoming higher. So what happens, your current increases, and you can see by this expression also. In expression we know that my forward current I is is exponential, okay, qv upon kt and kt. Okay, now when you are increasing temperature, this is increasing, so obviously your I should also increase, because I also depends on reverse saturation current in formula. Okay, so when you are increasing I, okay, your barrier width, I'm again writing here. Okay, this forward current increases with increase in temperature. Okay, because your width get decreases, band gap gets decreases, band gap decreases, electron energy become higher, electron energy increases. Okay, so flow of current increases. Okay, now let me explain the breakdown voltage. Okay, now why breakdown voltage is increasing. Okay, so first of all, we have to understand what is breakdown voltage. Okay, what is avalanche breakdown. Okay, so in the case of avalanche breakdown, okay, so avalanche breakdown voltage, okay, VB increases with temperature. Okay, that means your VB, okay, has a positive temperature coefficient. That means your delta VB by delta T is positive for avalanche breakdown. Okay, so the temperature coefficient of VB is positive. Temperature coefficient, okay, of avalanche breakdown. Okay, avalanche breakdown voltage is positive. Okay, now let me explain what is breakdown voltage, how breakdown happens. Okay, so in the case of, you have a semiconductor. Okay, you have a semiconductor. Okay, so you have, okay, so when at T is equal to 0, you don't have any electrons. Okay, but as you increase the temperature, you have some free electrons. Okay, so what happens when I increase the temperature. Okay, so when I increase the temperature, this ionization energy increases. Okay, the this velocity of this electron increases. Okay, so when this electron with higher energy, they impact these bonds. Okay, so you have electron, when temperature increases, okay, temperature increases, the electron energy increases. Electron, okay, energy increases. Okay, not temperature, no, sorry, not temperature, when you increase the voltage. Okay, when you increase the voltage, okay, when you increase the voltage, what happens? Your electron energy increases. So this higher energy electrons, okay, that they get collide with this bond electron, this uh, valence electrons, or it's bonded electrons. Okay, so when these electrons collide with these bonds, okay, they break these bonds and they make more free electron available. Okay, so for example, you have a one electron. Okay, this electron collides with another electron here and it makes him free. So one electron produces two electrons. Okay, similarly this two electron produces two more electrons. Okay, and again these two electrons again produces two more electrons. Okay, so what happens? You have now, let me draw it properly. Okay, so you have a one here electron, you have two electrons. Okay, now these two electrons are again creating two more electrons. Okay, so now you have four electrons, and these two electrons again creating two electrons. Okay, so what happens? So slowly what happens, that your number of electron gets increased. Okay, so this is called impact. Okay, this is called impact ionization, because as you increase the voltage, electron energy increases and they ionize band. Okay, so this way cascade process started. Okay, so this phenomena is called impact ionization. Impact ionization. Okay, now because of this impact ionization, okay, uh, your electron is getting energy from field and it is breaking this bond, and you have a large current in the IV characteristic. So if you increase the voltage at a particular voltage, okay, lot of charge carriers are get free, and now these free electrons have sufficient energy to break the bond. So suddenly at particular voltage your current gets increases. Okay, now what happens when I increase the temperature? Okay, so when I increase the temperature, obviously now this scattering will increase. Okay, so suppose first initially my uh, electron is moving with say 1 mega electron volt energy, or that 1 electron mega is too high, so it's particular, some for example it's moving with high energy. Now if you increase the temperature, so increase the temperature, what will happen? Scattering will increase. So scattering will increase. So what will happen? They collision, the electron will collide with the this phonon lattice, so their energy get reduced. Okay, so now same voltage will not be sufficient to make breakdown. Are you getting? As I am increasing the temperature, okay, as I'm increasing the temperature, okay, phonon lattice vibration increases. Lattice vibration increases. Okay, and when lattice vibration increases, okay, this scattering also increases. Electron scattering also increases. Scattering also increases. Scattering increases. Okay, so scattering increases means now electrons are losing energy. Okay, so losing energy means now this voltage is not sufficient. Now if you want to make breakdown, you have to increase the voltage. Okay, so that's why if you increase the temperature, okay, for same ionization to take place, so same breakdown to take place, you now need to increase your breakdown voltage. Okay, this point is clear?
Sir,
Sir,
sir, scattering increases because of which, why it makes this?
Because you are now vibration amplitude increases. Lattice vibration is what? If you increase the temperature, okay, this vibration amplitude increases, so now there is more probability of scattering. Okay, there are more collision, so electron are gaining energy but it's colliding more compared to previous case. Okay, so you're losing more energy, so now you have to push electron more. That means you have to further increase the reverse bias voltage. Okay, then only breakdown can take place. Okay, yes, any other question?
sir, why electrons are losing energy?
Because of scattering, na? Electron, what is the resistance? The resistance is because your electron get colliding with this thermal lattice vibrations. Okay, so as temperature increasing, now we are increasing temperature. I have discussed so many times these things. Okay, when you increase the temperature, lattice vibration increases. Okay, so amplitude of vibration increases, that causes probability of scattering more. Okay, that means more scattering. More scattering means now the electron loses energy frequently. So that means this voltage is not sufficient to break the bond. You have to increase the voltage. That's why your avalanche breakdown voltage increases with temperature. Okay, it's a positive temperature coefficient. So now what happens in Zener breakdown? Okay, so now if I say my breakdown is Zener breakdown. Okay, so Zener breakdown voltage, let me first write, then I'll explain. Zener breakdown voltage has negative coefficient of temperature. Okay, that means now your Bj, okay, Zener breakdown voltage, I say Bbj, okay, that decreases with increase in temperature. Okay, now why it happens so? So Zener breakdown has a different mechanism of breakdown. Okay, so when I apply normal breakdown, okay, so your breakdown happening somewhere here, higher voltage. Okay, now in the case of Zener breakdown, so what is Zener breakdown? So Zener, can I erase this one? Okay, so in the case of Zener breakdown, you have a PN junction with very high doping. Okay, so you have this PN junction, okay, with very high doping. So when doping is very high, in that case here the width is very small. Okay, so in Zener breakdown, okay, because of high doping, Zener diodes have a high doping. Okay, so Zener PN junction or Zener diodes, okay, Zener PN junction has high concentration, okay, high concentration of impurity. Okay, so when the doping is very high, okay, or you can say doping is high. So when doping is high, okay, we have seen the width of depletion layer decreases. So width of, when doping is high, okay, doping is high, so width of depletion layer decreases. Okay, now here we have electric field. When you are applying reverse bias, when I'm applying reverse bias, here we have electric field. Okay, now this electric field depends on what? Width. Okay, so electric field is what? Electric field depends on width. How can I write electric field? How can I write electric field? B by W. Okay, so inside the field, okay, this electric field depends on your W. If W decreases, your this E increases. Okay, now for example, you have this type of Zener breakdown. Okay, so in the case of avalanche breakdown, you need higher voltage, but because Zener में क्या है कि width कम है, so the lower voltage is sufficient to make breakdown. Now this width, when you increase the temperature, this width go down more. Okay, compared to this is already very thin. Okay, so there's a very high electric field. So now this high electric field is sufficient to break the bond. Okay, so in the case of avalanche breakdown, you have the mechanism of breakdown is impact ionization, while in the case of Zener breakdown, the breakdown is assisted by a electric field. Okay, so this is the electric field assisted breakdown. Are you getting my point? Here your electrons are not getting energy in breaking the bond. For that you need more breakdown voltage, more energy. Okay, but in the field itself, because the width is small, inside the width, field itself is sufficient to break the bond. Okay, so electric field, this is the electric field assisted breakdown. Okay, now when you increase the temperature, this width reduces, so your electric field become more strong. So earlier you need some electric field, say E1. Okay, E1. Now you don't need E1. Now you need E2, which is less than your E1. Okay, because now your temperature increasing, the width is decreasing, so your electric field is increasing. Okay, that means now you can reduce this voltage. There's a reverse effect. Are you getting this point? Okay, are you comfortable with this explanation? I am increasing the temperature, this width decreasing. Okay, so my field increasing. So now earlier this field was sufficient to break the bond. Now field become more, so you can slightly reduce the voltage. Still breakdown will happen. So Zener breakdown has a negative temperature coefficient of temperature. Okay, so any doubt you can ask me.
Sir, in between
Sir,
you
yeah.
said
Yes.
that electric field assisted breakdown.
Yes.
It is not electron, but electrons are the one which produces, na? So what is
No, electric field. See, inside the depletion region may be the electric field, hai na? And the electric field also can break the bond. The one mechanism is impact ionization. Impact ionization, your electron are gaining energy and colliding with bond. And the second mechanism, electric field itself is very high, and this width is so small that voltage, okay, whatever voltage applying, is creating maximum electric field inside. That electric field itself can break the bond. Okay, and you can get a lot of free charge carriers, so your current increases. That's why Zener breakdown, this happens at lower voltage, okay, compared to your avalanche breakdown, because in the case of Zener you have this width is small. Okay,
सर जेनर में ब्रेकडाउन वोल्टेज डिक्रीज होता है.
Zener breakdown voltage decreases with temperature. So these are only facts you to remember if they can ask small questions, okay, based on facts. So this part is completed. Okay, let us do some problem. So it says silicon diode has a saturation current of 7 microampere at room temperature. Okay, so you have been given room temperature, say at 300 Kelvin. Okay, you have been given IS1 is equal to 7.5 microampere. Okay, now you increase the temperature up to 400. Okay, now temperature is T2 is 400 Kelvin. Okay, so now what is the value of I saturation current? Okay, tell me what is the value. So what is the formula?
IS2 is equal to IS1.
Okay,
2 to the power T2 minus T1 upon 10.
okay, so 400 minus 300 upon 2, 10. Okay, 10. So IS2 become IS1 is just 7.5 microampere. Okay, into 2. Okay, so you have 100 difference. So 100 divided by this, so 2 power 10. Okay, so 7.5 into 10 raised to power minus 6, और 2 power 5 10 कितना होता है?
1024.
1024. Okay, 1024.
24.
Yes. So you solve this one. How much is coming? It should come around 7.6 milliampere.
Yes, sir.
Okay, 7.6 milliampere, 68 something. Okay, approximately 7.6 milliampere. Okay. Now question second is find the voltage at which the diode current is 90% of its reverse saturation current. Okay, so you know the current formula, IS exponential, okay,
सर क्वेश्चन एक और बार।
हाँ बोल रहा हूँ, एन वी टी, okay, what is the formula for this one? Exponential, okay, minus 1, this is the current, okay. So it says the diode current, find the voltage, okay, find the voltage V, okay, at which this diode current का मतलब forward current, the diode current is 90% of its reverse saturation value, okay. So diode current is the 90% of reverse saturation current, that means it is a 0.9 is. So you're asking basically at what forward voltage the current will become 0.99 is, okay. So you need to calculate the voltage. Here I want to mention one thing, okay, that's a very important thing. So whenever you have to calculate reverse voltage, okay. So suppose you have been given current, if you are asked to calculate the voltage, then either you put minus here or minus here. If you put minus here, automatically minus will come here, okay. Don't put the minus simultaneously, then the question will become wrong, okay. So whenever you have been given reverse saturation, reverse current value, that you put it with negative sign, and the voltage will automatically become negative. And similarly, if you put voltage negative here, your I will become automatically negative. So when you're calculating for reverse voltage, don't put sign minus both sides, okay. So this is for forward. Forward we know V is positive, I is 0.9. You can find the voltage value now. So you want to find the voltage, okay. So this is given 0.9 is, okay. Temperature also may be given in the question. So temperature you can take eta equals to 1, okay, eta equals to 1 in the question, okay. And you can also take your Vt is equals to 0.06 volt, that means 26 millivolt, okay. So now you want to find exponential, so open this one, so this become exponential. V eta is 1, Vt is given 0.26 minus 1, okay. Is cancel, so this 1 goes there, so you have exponential V upon 0.026, okay, equals to 1.9, okay. Now if you want V, so V become ln 1.9, okay, into 0.026. Tell me what is coming. ln 1.9 to 1.9 की वैल्यू कितनी है? This should be 0.026 and this should be around 0.6. Check it. 0.6.
0.16 our answer.
So this is 6418 and the answer should come your 0.016, okay, 0.01668, okay, 1668 voltage, okay. So it is very low volts.
0.016 ना सर?
हाँ जो भी है ऑलमोस्ट इतना आएगा 0.016. You can check the answer, okay. तरीका बता दिया मैंने आपने, कैलकुलेशन you can check.
Correct है सर.
Now second question is again asking that a germanium PN junction is given, okay, and asking find out the reverse current, okay, find the voltage, okay, find the voltage at which reverse current becomes 90% of is is, okay. So again current is given, this 90% of this one, but this is a reverse current, okay. So this time they given find the voltage at which reverse current become this one. So whenever they give a reverse current, okay, you have to put with minus. This become 0.9 is. Okay, is exponential. Okay, so this will automatically become negative. Don't put minus here. Okay, so you get V eta is given same is 0.026 minus 1. Okay, this become reduces.
सर जर्मेनियम के लिए ईटा 2 नहीं होगा?
Germany beta is 2 ना?
जर्मेनियम के लिए इसमें क्वेश्चन में 1 दे रखा है. ओके, इस क्वेश्चन पर्टिकुलर क्वेश्चन में उन्होंने 1 दे दिया है, तो जर्मेनियम के लिए 1 बोल दिया इन्होंने. ओके, जर्मेनियम के लिए 1 ही होता है, सिलिकॉन के लिए 2 होता है ना. वैसे भी तो जर्मेनियम के लिए तो 1 ही होना चाहिए. करंट तो जर्मेनियम में ज्यादा आएगा ना, जर्मेनियम का बैंड गैप कम है.
Yes, sir.
So if I write exponential, okay, V upon 0.026. Now how much I'm getting? I'm getting this 0.1. Okay, so V will come now 0.026 into ln, okay, 0.1. So how much is coming voltage? Now automatically is 0.1, so answer will come negative.
Minus 0.05986.
Minus 0.
0.05986.
5986. Okay, others also can check. Just give me 1 minute. Now it says if the reverse saturation current of p junction silicon diode is 1 nanoampere. Okay, so now is value is given 1 nanoampere, that means 1.9 ampere. Okay, if I ask find the applied voltage, for which a forward current I is equals to 0.5 microampere, that is 10 to power minus 6. Okay, now you have been given, you have to find the voltage value. Okay, eta value is given 2, temperature is given again 300 Kelvin. That means you can take Vt equals to 0.026 volt. Find the voltage. So you have been given is. Okay, you want I forward. Okay, is is your 1 into 10 to power minus 9. Okay, exponential. Okay, you have V upon 2.026. Okay, minus you can leave for forward current. Okay, because forward current one is negligible. If you want, you can put 1 also, but that will not affect your answer. So here you can write 0.5 microampere. Okay, so this power cancels -6, you have -3 here. This go down, so it becomes 0.5. Okay, this become 10 to the power 3 here. So this become 500. 500. Okay, exponential v upon 2 into 0.026. Okay, so if you keep 1 also here, then it is this become 501. Are you getting my point? Okay, so that will not affect much. If you calculate, keep 1 also here, okay, then this become only 501. Okay, plus 1. So इसमें ज़्यादा difference नहीं आएगा. Okay, so you want v, so your v will be 2 into 0.026 ln 501. Okay, tell me answer what is coming.
0.32 millielectron volt.
Okay, so check the answer. 0.3, yes, 0.323. Okay, so answer should come 0.323 volts. Okay, so students, so this chapter is finished. Okay, now we will start now diode. So tomorrow onwards we will start your diode. Any question? Any question?
Sir,
Hmm.
sir, I have a question for Fermi level.
हाँ.
So Fermi level dependence on temperature. एक क्वेश्चन था गेट का, old
हाँ.
question.
हाँ हाँ हाँ. So उसमें क्या था?
सर वहाँ पे कंसंट्रेशन दिया हुआ है, एनसी दिया हुआ है और कहा गया कि टेम्परेचर इंक्रीज हो रहा है, तो आपका फर्मी लेवल कहाँ पे चेंज होगा?
भी अगर एन टाइप मटेरियल है तो फर्मी लेवल डिक्रीज होगा. ओके,
सर हमारा जो यहाँ वो था, इक्वेशन था EFI प्लस KBT LN
यस.
NC by NI, उसमें तो इंक्रीज हो रहा है ना सर?
No, you have EFN. Okay, that is what EC minus KT ln NC upon NC upon क्या है?
NI.
NI.
सर वो प्लस है. EFI. EFN Fermi level n-type material ना. Fermi level cannot be greater than EC ना. Fermi level always less than your conduction band. हाँ सर, एक और एक इक्वेशन था ना, दो इक्वेशन था.
So that equation is your EFN is equal to EFI plus KT ln ND upon NI. Okay. Okay.
So this will be NC by ND.
This will
First one.
This will be NC by ND.
ND.
And this is ND by NI.
NI. Yes sir.
So here this is the intrinsic Fermi level na.
Yes sir.
This is constant. Okay. This is the Fermi. This is the mid of the thing. They're asking what happens to this Fermi level. Okay. So this Fermi level, when you increase the temperature, okay, so this should decrease. If you increase the temperature, this should decrease. Okay, let me check this one. EFN plus KT ln ND upon NI. So when you increase the temperature, what happens? Your NI increases, na? Your NI increases. So this overall term, okay, here more than temperature, this log term is dominating. So when you increase the temperature, okay, your material becomes more and more intrinsic. So material become more and more intrinsic means your Fermi level should go down. And P type it will go up. So whenever you increase temperature, now this material will try to become intrinsic. N type it will come down and P type it will go up. Okay.
Okay sir. Okay sir.
You can check from here.
Okay sir.
Okay. So tomorrow onwards we'll start your diode. Okay. So I'm stopping here. Thank you very much.
Thank you, sir.